So any questions? I mean, we started discussing the SU3. By the way, for the homework, I mean, submitted on Friday, and essentially, I mean, since we didn't do this chapter 7, so just do the chapter 5 and 6 for this Friday. Chapter 7 we just did a little bit, I mean, not really in detail. So. And regarding the grading system, so it will be roughly like 25% for the homework and 75% for the exam. So that would be the roughly. I mean, could be 70-30 or 75-25. You know. Okay.
How will the homeworks be evaluated?
I think based on, okay, you have to submit, of course, the homeworks, and so the submission of that I mean, you do everything, and the performance in the class, you know. So it's an overall impression. I mean, it's not just the homework. I mean, it's not like grading of the homework is not the important part. That the main thing about the homework, of course, is that I mean, that is the way to learn the subject, really speaking, right? So unless you start solving problems, you don't really understand the subject. Right? I mean, you see, you may think that you understand it, okay? But when you start solving, then you know some of the doubts emerge. You know, some of the things which are not completely clear to you, that you know that emerges, and then that is the way to learn. For me, I mean, grades are not the important thing. The important thing is you should understand the subject. Okay. Grades are important in a certain sense when you start applying for the you know PhD positions and things like that. So they will see the transcript of the grade. So it is important in some sense, but ultimately, I mean, for that is so like a. But ultimately, for the research, which is what I suppose most of you are going to do, right? To do research, what is important is understanding the subject. But yeah, it is practically it's of importance to also get good grades. Good. So SU3. So we started. Yeah, let me just write down somewhere those these generators. So we had lambda 1, which was 1. No, yeah, 0, 1. Lambda 2 was 0 minus 1. Lambda 3 was 1 minus 1. Lambda 4. Lambda 8 is 1 over 3. Okay. So these are the Gell-Mann matrices, and this normalization is just done so that this normalization is just done so that the trace of lambda A, lambda B was 2 times delta NB. It's not necessary. I mean, you could have chosen any basis. It doesn't matter, so long as it spans the entire space. No, you could have chosen any basis, but it is just a convenient basis. Okay, and what we saw last time was that there was, I mean, a curious feature was that if you take, for example, this guy, and that guy, this forms an SU2 subalgebra, right? You can actually look at the commutation relation. Lambda 1, lambda 2 commutation is just 2i. I mean, they are just sigma matrices after all. If you forget the third row and third column, this is sigma 1, sigma 2, and sigma 3, right? So in this commutation relation, you will exactly get the thing that you had for the sigma matrices. Okay. Yeah, I've just written one of them, but you can see all of them will satisfy the SU2 algebra. Same thing with this guy this guy, and a certain combination of these two, the combination such that the only non-zero entries are the here and there. This becomes 0, right? Then that combination will again satisfy an SU2 subalgebra because we can just delete second row and second column. It's again the Pauli matrices, right? So to be able to delete the second row and second column, that's what I'm saying, that you have to take some combination so that this element becomes 0. No? Middle element becomes 0, which you can always do, right? I think it was simply lambda 3 plus root 3 lambda 8 divided by 2. Divided by 2 so that 1 plus 1 is 2. Divided by 2 makes it 1. And so lambda 6, lambda 4, lambda 5, and this combination exactly are the Pauli matrices where when you have eliminated the second middle row and column. No? So they will satisfy again an SU2 algebra. And finally, if you take lambda 6, lambda 7, lambda 6, lambda 7, and then take the opposite combination which removes this entry, which will be lambda 3 minus, maybe it's other way around. Okay, I'm not sure. Root 3 lambda 8 over 2. Maybe it's a plus or minus. I mean, this will be either plus or minus sigma 3. Okay, if you remove the first row and first column. You can work it out. So this will again form another SU2 subalgebra. So we see that there are these various SU2 subalgebras, and this will be very useful for us. I mean, we will be because we know everything about SU2, right? Now, all the finite dimensional representation we know, so that will be very useful. Okay. So then just like now how do we proceed? Like in SU2, what we did, we first looked at the Cartan subalgebra, which was in that case was one-dimensional, right? And we could choose the sigma 3 as a generator of the Cartan subalgebra, and then find the eigenfunctions, right, of the adjoint representation. You remember we constructed E plus and E minus, which were such that the commutation relation with sigma 3 was giving you back again sigma plus and sigma minus with some eigenvalue, right? So that is the next step you want to do, because those E plus and E minus were playing the role of raising and lowering operator, right? So that will be again very useful here. So what are the, let's say, first of all, the first task is to find the Cartan subalgebra, which is clear here. I mean, a natural choice is just to take the diagonal elements. So take diagonal matrices here. Because the diagonal will of course commute with each other, which are, in this case, is this lambda 3 and lambda 8. Right? So Cartan subalgebra in this case is two-dimensional. So an arbitrary element of Cartan subalgebra would be some combination alpha lambda 3 plus beta lambda 8. Right? So this will, alpha and beta are arbitrary numbers. Right? So this will span a two-dimensional space. And this commutes. So this is an abelian subalgebra. Okay? So Cartan subalgebra is always a maximal abelian subalgebra. Maximal means that I cannot add to this anything else. You see, if I have chosen this and this, then the question is, could I have added any of the remaining ones? Well, if you add that, then it's no longer commuting. Okay? Because any of these guys, lambda 1, the remaining ones, it will not commute with both lambda 3 and lambda 8 simultaneously. No? So therefore, that is, so you cannot add anything else. Cannot add to this list any other generator. Because if you do that, then it is no longer abelian, and therefore it is not a Cartan subalgebra. So it is Cartan subalgebra. The dimension of the Cartan subalgebra, there's a name for that. Dimension of this Cartan subalgebra is called the rank. Rank of the algebra. It's just a name, definition. Rank of the subalgebra. Rank of the full algebra. Rank of, let's say, G. G is the full algebra. Okay. So once we have done this, the next task is to construct the analogues of the raising and lowering operators. Analogues of raising and lowering operators. So how do we do this? Well, let us look at, for example, this subalgebra, SU2 subalgebra. Then we already know, because this is sigma 1, this is sigma 2. So sigma 1 plus I sigma 2 and sigma 1 minus I sigma 2 will be eigenfunctions with the commutation relation with lambda 3, right? So if you look at the commutation relation, so if I write, maybe I should follow the notation which has been used here. Yeah, so right, so we choose, let's say, so we define, maybe here it says that, right? So x alpha 1, this nomenclature, this notation will become clear in a moment. So we just take it to be one half of lambda 1 plus I lambda 2, and x. So I can write both of them, plus minus alpha 1 as plus minus alpha. So that's that. So which will be, in this case, if I have a plus sign, I will have 0, 1, 0, 0, 0, 0, 0, 0 for the plus sign. For the plus sign, and for the minus sign, it will be 0, 1, 0, 0. Just because you can see when you add plus I. Oh no, maybe it's the other way around. No, it's okay. When I multiply by I here and add that up, this adds up, whereas this cancels, right? So I'm dividing by 2, so it again becomes 1, right? And similarly with a minus, this will cancel. If I multiply, if I take the minus sign here, this will cancel, but this will add up, and it gives you a factor of 2, which cancels from this one. So that's that. Then x plus minus alpha 2 will be, so we are looking at, let's see, this ones, right? So we're looking at lambda 6. So this will be lambda 1/2 of lambda 6 plus minus I lambda 7. And finally x plus minus alpha 3 equal to 1/2 of the remaining guys, lambda 4 plus minus I lambda 5. So these combinations. So these combinations will be, one can check quickly that these combinations are in fact eigenfunctions with respect to both of them simultaneously. You see, both of them. Okay. So for example, let's see. If I take lambda 3 with the x plus minus alpha 1, or maybe should I do with lambda 3 over 2 perhaps? Oh, that's a matter of normalization, but let's see what is the normalization here. H1.
We are considering the fundamental representation.
No, adjoint representation. We are looking at the adjoint representation because, yeah, that maybe I should have mentioned. What we are looking at is the adjoint representation because it was an adjoint action. So add x acting on y. I mean, x is an element of, so x is an arbitrary element of the Lie algebra, but y is also an arbitrary element of the Lie algebra. So the space on which this operator acts is the Lie algebra itself. So it has the same dimension as a Lie algebra. So in the SU3 case, this will be an 8-column vector because there's an 8-dimensional vector space, right? So this is going to be, is defined as a commutator of x with y. Okay. This is also in the Lie algebra element. So this, you see, add x maps Lie algebra to Lie algebra. Considered as a vector space. So this is 8-dimensional space is mapped to 8-dimensional space. So if you, and this is a linear map, of course. So if you if you wish, you can write it as a matrix, because any linear action on a vector space, you can always write it as a matrix multiplication. No? So this would be then 8 by 8 matrices. So we are looking at the adjoint action. And what we are asking is that if I look at the adjoint action of lambda 1 and adjoint action of lambda 2, lambda 8, then, so each of them is an 8 by 8 matrix, right? We want to diagonalize these matrices so that, in other words, eigenfunctions of these matrices.
Lambda 3. Instead of lambda 1.
Lambda 3, sorry, lambda 3. Yeah, lambda 3, correct. So we want to, diagonalize lambda 3 and lambda 8. Right? So that is what it will happen, right? I mean, if I can find an eigenfunction, lambda 3 with x, some combination of various guys, is equal to some number times x itself, I mean some number times x, and simultaneously lambda 8 commuted with x is again some other number times x, then you see we have found an eigenfunction, a simultaneous eigenfunction of both of them, right? Because add lambda 3 acting on x is by definition this, right? And similarly add lambda 8 acting on x is by definition that. So we want to simultaneously diagonalize the two things. And this is possible because they commute with each other, you see. If they were not commuting, you could not have done that, to find simultaneous eigenfunctions. Now we can find simultaneous eigenfunctions because they are commuting with each other. Okay, so then let's just, what is H1 and H2 here? Okay, so in this notation, so what one is doing is one is choosing a basis, not this lambda 3, lambda 8, but choosing the basis where H1 is lambda 3 itself, but H2 is a certain combination. I think it is this combination. Okay, lambda 3 minus root 3 lambda 8 over 2, because lambda 3 minus root 3, this cancels, so you get here, perhaps it's overall minus sign. Minus sign. Okay, so explicitly this is the matrix 0, 0, 0, 0, 1, 0, 0, 0, minus 1, and that is the lambda 3. I think this is what we are using as a basis. It's not important. It's not important because if we have diagonalized both of them, then obviously we have diagonalized lambda 3 and lambda 8, right? In fact, any combination of these guys we have also diagonalized, right? So it's just a matter of choice. I mean, a convenient choice, or in fact, what I will do is I will also. Okay, it will turn out that if I look at the eigenvalues with respect to lambda 3 and lambda 8 instead of H1 and H2, you will get some nice pictures. Okay, whereas with this choice, the pictures will be a bit distorted. You will see the pictures now, probably, hopefully by today. All right, so let's just write down the eigenvalues here. Let's see, is this here? So choose the. I've written already here. So this guy. So this one. This. Let me write it. I erased this part. No, this part I erased. I mean, x plus minus alpha 2 is 1/2 of what is it? X plus minus alpha 2 is in this block, so it is. It's I think this combination. So lambda 6 plus minus I lambda 7. And x plus minus alpha 3 is equal to 1/2 the remaining ones, lambda 4 plus minus I lambda 5. There is a reason for this notation which will become clear, plus and minus. Well, plus and minus are raising and lowering operators, but okay. Okay, so if I just let's try to write down a few things, because then there is an exercise here to. Let's just work out one particular thing. So I want to compute, say H1 with say x plus minus alpha 1, the commutation relation of this. So because that's a adjoint action, so we're looking at adjoint action. Right? So that's the same as so very right. So what we can, I mean that is H1 is simply lambda 1 itself, lambda 3 itself, and this is this combination lambda 1 plus minus I lambda 2 just makes it the sigma plus and sigma minus, right? So that commutation relation we already know, it's plus minus, sigma plus minus. So it is plus minus 1 times x plus minus alpha 1, right? 1 is the number and the eigenvalue. Whereas if you look at H2 acting on x plus minus alpha 1, this you see H2 is that. So you will, let's see, is there some simple way of doing it? So I mean, let's just write down, let's just work it out. 0, 0, 0, 0, 1, 0, 0, 0, minus 1. That's H2. And x alpha plus minus alpha 1. So let's say plus alpha 1 corresponds to 0, 1, 0, 0, 0, 0, 0, 0, 0, right? And I have to take the commutator of these two matrices. Let me just work it out explicitly. So when I multiply this way, so I'll get here 0, 0, 0 from the first row. The second row is also 0, 0, 0, and third row is also 0, 0, 0, right? When I multiply that like that, because this one will hit only the second column to be 0. But then I have to multiply other way also, right? So I take this with that is 0, but this with that is what is it? This with that gives you 1, right? 0, 1, but with a minus sign here, and then this with that is 0. This with that everything is 0, and this with that is also 0. Okay? So altogether you get a minus, right? Minus times again the x alpha 1 itself, right? So you get here, is it correct? No, sorry, here should be 2, plus minus 2, right? Because I have not divided by 2. This is not, I mean, in the previously we had divided sigma 3 by 2. So this would be plus minus 2, and here I will get minus plus times 1 plus minus alpha 1. Okay. So important point is that both, I mean up to some numbers they give you back the same guy. So this is simultaneous eigenfunction. Okay. Alpha 1. And similarly, you can work out, I don't know if the answers are given here. Answers are, I think, yeah. So then there's a notation here which I'm going to use now. So from this, of course, I can read out, right? So if I of course, the Cartan subalgebra is generated by these two guys, H1 and H2. So in general, if I take any element A, H1, I think here I'm using the word A and B. AH1 plus BH2 is an arbitrary element of the Cartan subalgebra, right? Of course, this will also be diagonal because each of them have become a diagonal. A joint representation has become diagonal matrix. Yeah.
Here we are constructed the raising lower operators using the fact that in our generators of the German matrices there is Pauli matrices. But in general, how do we construct the raising and lowering operators?
Yeah, we'll see. I mean, so the next once I finish SU3, then I will go to the general Lie algebra structure. Huh? So we will see that in general this will be possible.
Do we have to always construct them by pairs?
Well, I mean, let's see. I mean, when we go to the general formalism, you don't need to know anything about too much about explicitly writing down the matrices and so on. Is not important. You know, you will see that in general you can. I mean, at the moment I have not defined the roots and so on, but we'll see by the end of today's lecture we will introduce a lot of new definitions, and then there is a way you can prove in general that you can always split the roots, different eigenvalues, in terms of something which we call positive and something which we call negative. That's up to you. I mean, which one you call positive. So there are many. It's not unique choice. No? I mean, so half of them are positive and half of them are negative. So positive ones you call them as raising operators, and negative ones lowering operators. So because here you see, I mean, it's not that just a plus sign here, no, but here is a minus sign, no, for the plus alpha one. So it's not so much the plus everything should be plus. It's up to you. You can define in different ways. So if I look at now, so this is now we are looking at add of this guy, right? But of course, this by linear action, this is nothing else but A add H1 plus B add H2. So then the eigenvalues will just add up, right? So eigenvalues. So for example, now suppose I want to ask what is this guy. So add of this object acting on x plus minus alpha 1, right? That's going to be A times the eigenvalue with respect to H1, which is this. So let me write it as plus minus 2A, right? And then minus plus B, because that is minus plus 1 times B. So that will be the eigenvalue. So actually, let me just write it like this. So I take out this plus minus, so this becomes minus B, right? And then x plus minus alpha 1. So now this is an important concept here, so what is this doing here? So you think about, so these are called roots, by the way. These are called roots. And what is root actually doing, right? It is associating to any element of the Lie algebra, Cartan subalgebra, a number, right? Take any arbitrary Cartan subalgebra element, and once you specify this particular x plus alpha 1 or minus alpha 1, then you get a number. Okay. So what we see is that now this notion, I don't know if you have. Let me see. Are you familiar with the notion of dual vector space?
Yeah.
Huh? Yeah. So everyone is familiar with dual vector space? Let me repeat this again. I mean, even if you know, just to. So what is it? I mean, if you look at, suppose I'm given a vector space V, some, let's say, k-dimensional vector space. Okay. Then, and consider the set of all linear functions. Okay. So a function is what? A function is something that for every vector V, every vector inside this V associates a number, right? A number. Well, I mean, if it could be real vector space or complex vector space. If it is complex, it could be complex number. Real vector space means real numbers. That's what the linear function. A function does that, no? For every. Now, what we want is a linear function. Okay. A linear function means that if so let me call this function f, then f of a v1 plus b v2, where v1 and v2 are elements of v, some v, v1 and v2 are elements of v. Then of course linear combination also belongs to v, because this is a vector space. So this function f will give me some value for this, some number for this, right? But that number has to satisfy this condition that it must be a times f acting on v1, the function acting on v1, plus b times function acting on v2. Okay. That's what it means linear, the usual linear definition. Then and now you consider the set of all such linear functions, not just one linear function, but the set of all linear functions. Okay. The set of all linear functions, that is what is called the dual vector space. So now you consider the set of all linear functions, and that is called first of all, let me make one more statement before I say this. And now suppose I am given two linear functions, f1 and f2. So suppose I'm given two linear functions. Okay, let's call it f1 and f2. Okay. F1 and f2 both satisfy this linearity condition, right? Because that's by definition linear functions. But if so, I can construct another linear function which is simply a linear combination of them, right? So any alpha times f1 plus beta times f2 will again give me linear function.
Vector space.
Yeah. So therefore, the set of all the linear functions forms a vector space, because we have all the properties of the vector space here, right? The zero function would be something which gives you zero for everything. No? For every element in V, the zero function is the one which maps every vector in here to the number zero. Okay. So this forms a vector space by itself, the set of all linear functions, and it is not hard to show that the dimensionality of this vector space is the same as the dimension of the original vector space. Okay. It is simply, you can just do the following and choose a basis for this, right? Let's say I choose a basis E1 up to EK, if this is k dimensional, right? Then I can define, I can define a linear function. Let me call it Fk, Fj, and Fj has a property that acting on Ei gives you delta Ij. Okay. Then any function you can write as linear combination of these Fj's, right? You can easily convince yourself. So therefore, the dual space has the same dimension as the, because Fj, J also goes from 1 up to k. So, maybe you can try to prove that any function f, any linear function f, can be written as linear combinations of Fj's. Okay. It's easy. So therefore, you have an explicit basis for this this dual the space of linear functions, which also is k dimensional, because there are precisely k of them. Right? So the dual vector space has the same dimension as the. Okay. Now, using this language, you can call this eigenvalue that you get here as an element of the dual vector space. Okay? Because for any element of the original Cartan subalgebra is my original vector space. So Cartan subalgebra in this particular case was two-dimensional, right? And what we have is that we are associating a number for each of this element here. I am associating a number, and it's a linear map, because you see it's coming. Any combinations A and B is just coming linearly with A and B. So it's a linear function. So these alphas, this eigenvalue, these belong to. Maybe we should put some names to this. Okay, if I use the same convention, Cartan subalgebra, we are using the. This is hard to. The script H, unfortunately, I don't know how to write it on the blackboard. I don't know. Okay, I don't know. No, it doesn't look good. I want to distinguish it from small h, But how will you write it? Do you see this in definition 8.2? There is a script h, but I don't know how to write it. Maybe we should use some other name for it. Shall I just call C for Cartan subalgebra? Okay, not here. It's something which is hard to write. So let's say C, Cartan subalgebra. This is for Cartan subalgebra. Okay. Then this will be the dual space of the Cartan subalgebra, right? This function, this alpha. So I call this as alpha 1. Sorry, alpha 1. Alpha 1 belongs to the dual vector space.
What was the eigenvalue?
The eigenvalue. Okay. And the same thing will happen for all of these combinations which we have written down here. Alpha 1, alpha 2, alpha 3, minus alpha 1, minus alpha 2, minus alpha 3. Right? This is left as an exercise, actually. So just like here you have 2a minus b, you should be able to show that if I had taken I have applied the same combination, the same combination on x plus minus alpha 2, you have to show that this will, in this exercise 8.4, you have to show that this is plus minus a plus 2b x plus minus alpha 2, and when it acts on x plus minus alpha 3, this gives you combination a plus b plus minus a plus b acting on x plus minus alpha 3. Okay. So this is just like we explicitly calculated that. This exercise 8.4 is to show that also you have to do these calculations. Just compute the commutation relations to check what it is. So what we are seeing is that there are actually 6 roots. Okay? 6 independent roots because, well, independent meaning 6 roots. There are 2 here. One for plus, one for minus. And 2 here, plus and minus, 2 plus and minus. So there are 6 roots. And we have diagonalized all this, the Cartan subalgebra. Okay. And so Cartan subalgebra is, so the roots are this. So we have so many roots, alpha 1, alpha 2, alpha 3, and minus alpha 1, minus alpha 2, and minus alpha 3. These are the 3 roots. There are 6 roots. Right. For each of these, the remaining generators, once I have found combinations, which are eigenfunctions, since the remaining guys are 6-dimensional, total dimension was 8, right? FSU3. 2 is a Cartan, right? Now we are looking at the remaining part, and we are taking some suitable combinations so that they are eigenfunctions under the commutation relation. No? But anyway, it is 6-dimensional, so it has to be 6 altogether, right? And that's why we are finding the 6. These are 6 roots. This here now we are thinking of this as these are elements in the dual space of the Cartan subalgebra, which means these are linear functions on the Cartan subalgebra. Okay, so each of them is alpha I acting on a h1 plus b h2 will be some number. It's a linear map.
It just makes more sense that if we consider the operators themselves, the joint operators to be on the dual space because they are linear functions, but why the numbers themselves are?
Repeat that question again.
The numbers themselves, the alpha and alpha 1, alpha 2, they belong to the dual space. It makes more sense that the joint operators themselves is the ones who belong to the dual vector space because they are linear functions. But what does it mean for numbers to belong to a dual vector space? What does it mean?
It's not number. You see, this is a linear map, right? This by definition is alpha I. The fact that it's linear, it is saying that it is this plus b alpha I h2. Right?
Yeah, of course, it's like this because alphas are numbers,
Alphas are not numbered. Of course, it's a number in the sense that once you apply it on a particular vector in the Cartan, then it gives you a number, right? But if you change the Cartan element on which it's acting, it's going to give you a different number, right? So therefore, it's a linear function, right? And what we are seeing is there are 6 roots. Okay, these are all non-zero roots. None of this is a zero function. These are all non-zero eigenvalues. No? Okay. For some particular case, for example, I could choose b equal to minus a, then this vanishes, but not those guys. No? So not all of them are vanishing. No?
So by definition, the roots are the eigenvalues of the raising of Narain alternative.
Maybe at the moment let's not call it raising and lowering. in SU2 we call it raising and lowering because there's only one. I mean, there's only one SU2. Now it's much more complicated. There are 3 different SU2s, right? For each of them, there is one raising operator. So it is true that this plus alpha 1 and plus alpha 2 and plus alpha 3 will be raising operators for those 3 SU2s. If you just look at the 3 SU2 subalgebras, which we, these 3 SU2 subalgebras. Huh? But and minus alpha will be a lowering operator. Okay. But now we have a whole thing. It's all complicated. These different SU2s don't commute with each other. No? So it's not like direct sum of 3 SU2s. No? It's not the sum of the 3 SU2s. It's a much more complicated structure here. Okay. Now let me just try to plot this thing, and you see. I should just erase this part. What should I erase? So remember, what was it? This was. I want to plot the eigenvalues of lambda 3 and lambda 8, because then you get nice pictures because of that relation. Trace of lambda A, lambda B was 2 delta AB. So this is not properly normalized like this. So lambda 8, what did we say? Yeah, this is lambda 8 right here. So I can rewrite lambda 8 in terms of H1 and H2. So what is that? So 2H2. So if I take H1 minus 2H2, okay? If I take H1 minus 2H2, then lambda 3 cancels, and this becomes root 3 lambda 8. So divide by root 3, right? This is lambda 8. No? So let us just write down the eigenvalue for this particular object. So we'll write down 2 eigenvalues. I mean, the formula is given anyway here, so we just have to substitute that. Where is that? So alpha 1 on lambda 8. So let me write on both. On H1 is, of course, so lambda 1, which is the same as H1. H1, let me write H1. This is, we already see, so we just put A equal to 1 and B equal to 0 in this formula. So it's just 2. 2 x alpha 1. 2, it just gives you 2. And alpha 1 of lambda 8, where lambda 8 is that expression here. So I just have to substitute A equal to 1 over root 3 and B equal to minus 2 over root 3 in that general formula, right? So we will get here, what do we get here? So 2A, so A is 1 over root 3. So this becomes, is it correct? Is that correct? Sure. Is it true that this was H2 was given by minus sign, not plus sign? Lambda 3, no, it's a minus sign, right? It's a minus sign. I'm a bit confused here. The numbers are not coming out right. Let's see, what do we get anyway? I mean, if I just use this formula. So you get 2 over root 3. And then minus 2H2. Something is not right. I think it's minus. It's minus of that, right? It's minus of that. Okay. So that's correct, right? H2 is this because if I take this minus that, this it will become minus. I have to multiply by minus. So therefore, this is not correct. So what I should do, I should add it here, right? I should add it up, and then it's root 3. So that's correct. So it's that. So therefore 2 over root. So A is 2 over root 3. A is 1 over root 3. So that is 2 times A. I mean, this was when you write it. It was 2A minus B. But A is 1 over root 3. So 2 over root 3 minus b, which is again 2 over root 3. So this is 0. Okay. Right? So eigenvalue with respect to lambda 8 is 0. So all this is saying is, or what does it mean? It means that h1 commuted with x alpha 1 is 2 x alpha 1, and lambda 8 commuted with x alpha 1 is 0. Okay. There is 0 eigenvalue with respect to that. Okay. So let's just quickly write up all of these things. So what about alpha 2? Okay, minus alpha 1 and minus alpha 1 will be just some minuses of this, because it's always plus minus, right? So that we don't need to worry about. Once you have done for alpha 1, alpha 2, alpha 3, minus alpha 1, minus alpha 2, minus alpha 3 comes for free, right? So let's do alpha 2. So alpha 2 on h1 is simply minus 1, right? And alpha 2 on lambda 8 will be, so you have a is, so what is the value of, for lambda 8, a is 1 over root 3 and b is 2 over root 3, right? So just plug that here. So it's minus 1 over root 3 plus 2 over root 3, which is
Plus 4.
Root 3.
sorry
Root 3.
root 3, 1 over root 3.
Just root 3. Because it's 3 over.
I mean, it's a minus sign here, right?
Yes.
3 is, yeah, correct. 2 times 2, 4, sorry. Yeah, so 3 over root 3, which is root 3. And then we have alpha 3. Alpha 3 on h1 gives you, alpha 3 on h1 gives you 1. Huh? And alpha 3 on lambda 8 gives you the sum of the two, which is again root 3, right? The sum 1 plus 2, right? Is again root 3. So now let's just try to plot this. Huh? So what I will do is I will write down these eigenvalues. So I will plot the eigenvalues of h1 here. So these are the eigenvalues of h1. Eigenvalues for h1. And here I plot the eigenvalues for lambda 8. So the first thing for alpha 1, what we are finding is that this is 2 and 0, right? 2 and 0. So it's so it is in some units. So if this is 1, here you get. So this is alpha 1 because this component is 0, right? Lambda 8 eigenvalue is 0. Now let's look at alpha 2. You get minus 1. So I go back here, minus 1 approximately, and then root 3. So root 3 is somewhere here. So this is root 3, something like that here. Huh? So that's alpha 2. Okay. And then alpha 3. Alpha 3 is the same thing, but with the plus 1. So it's here. Okay. So this length is root 3. This length is 1. So let me just draw the arrow. So this is alpha 1, alpha 2, and alpha 3. Alpha 2 and alpha 2. Now, just by using trigonometry, you can see that this angle is 60 degrees. That's because this length is root 3 and that length is 1. So tan of this angle is root 3, and that implies that the angle is 60 degrees. And here it will be 120 degrees. This 120 degrees. Furthermore, the lengths, you see, if you look at the length of this thing, this is root 3. So use the Pythagoras theorem. 1 plus 3, 4. Square root of 4 is 2, right? So the length of this vector is 2. Length of this vector is 2, and length of this vector is 2. Okay. And then of course you have also the minuses, but minuses are just take the minuses of these vectors, right? So you get a nice hexagon. Yeah, so if you just this is just a regular hexagon. So this is a very this is a nice pattern which appears here for all the Lie algebras. Okay, this was because we chose this particular. We plotted like this alpha 1 and lambda 8 here, right? But I could have also plotted h1 and h2. No, then it will not be such a nice shape. Okay, it is simply because the normalization is different for the two things. If lambda 8 and h1 are orthogonal to each other, no, in terms of the trace. When you take the trace, so trace of h1 with lambda 8 was 0. Right? H1 was simply one of the lambdas, lambda 3. And the lambdas, so this was lambda 3, this is 0. Right? And furthermore, trace of lambda 3 square is 1, and trace of lambda 8 square is 1. This is why we are getting such nice pictures. For example, if I multiply lambda 3 by something, then this will look like a squashed hexagon, right? Because this length will become either longer or than that length, So this is the fact that we're getting such a regular pattern is because we have normalized conveniently. No, for that reason.
It's 2. The trace of the lambda squares is 2.
Sorry.
The traces of the lambda squares are 2.
2, correct. But yeah, the important point is they're all same. Yeah, they're the same. If there are different lengths. Different traces, then this will not be, this will change a bit. For example, I can change this number by multiplying lambda 3 with some number, no? I mean, say 10 times lambda 3 will have a trace, whatever, 100, 200, no? But if I then multiply, all the eigenvalues will multiply by 10. Right? If I multiply lambda 3 by 10, so then this length will become 10 times that, no? Whereas not that, if you don't change lambda 8, this will remain the same. Okay. So this picture is very regular because we have chosen a convenient normalization. Otherwise, it will be. But it doesn't matter. Whatever it is, what is the important point here? Yeah, and that's very important. That notice that if you add these two vectors, you get that vector. Right? I mean, that is a thing. So in fact, you could have seen it already here. What we are saying, alpha 1 plus, this plus that should be that, right? Which indeed you see, 2a minus a, 2b minus b is b. So this vector, alpha 3 is a combination, alpha 3 is in fact, in general, alpha 3 is alpha 1 plus alpha 2. As the linear functions, right? I mean, you see, the vector space was two-dimensional. Cartan subalgebra was two-dimensional. So alpha is living in the dual vector space. So alpha is also living in a two-dimensional vector space. Okay. So what we are saying is that as a two-dimensional element of the C star, these are all elements of C star. Okay. Alpha 3 is simply alpha 1 plus alpha 2. Okay. So you have a lot of roots. So these are not. It's not providing a basis for your dual vector space because there are 6 roots, right? Actual number of dimension of the dual space is only 2. So a lot of them are related to each other. No? Yeah. Okay. So this was the. Okay.
What's the significance of this hexagon?
Sorry.
What's the significance of this hexagon? You could have chosen different normalizations and obtained another shape.
Yeah, but shape is not so important. Important point is this is, once I have chosen a particular alpha 1, these are going to be, alpha 3 is, this will be always true, that alpha 3 will be equal to alpha 1 plus alpha 2, no matter what you choose.
So this in particular doesn't have any deep meaning?
No, but it's convenient to picture it, because at least for me, this shape stay in the mind, and the more regular the shape is, it stays longer. And you'll see that all the representations, fundamental representation, or all these representations come out when you write down their eigenvalues and plot it like this. Plot the eigenvalues with respect to the h1 and lambda 8. They come out like beautiful regular shapes, equilateral triangles, all sorts of nice shapes appear, which are easier to remember. No, no, otherwise it's not important. Yeah. The important point is this one. This one is true. No matter what basis you choose, it doesn't matter. This is still true. No matter what basis for the C you choose, that will still be true. Because that's a matter of function. Because you see, the fact that you're writing some, there's a function, these are all functions on the Cartan subalgebra, that does not depend on the choice of the, a given point in the Cartan subalgebra goes to some number. No? Now, what basis you choose in the Cartan subalgebra is irrelevant for that. No? So the basis is not important. Important point is that, so irrespective of the choice of basis, this is always true that alpha 3 for the SU3, alpha, the way we have defined this eigenstates, alpha 1, alpha 2, alpha 3, no? Alpha 3 is equal to alpha 1 plus alpha 2. That's the case. Okay, now let us, so fine, what we have done so far, we have done only part of the job, right? We have looked at the Cartan subalgebra, which is a set of maximally commuting subalgebras, and then we have looked at the adjoint representation and diagonalized this this Cartan subalgebra elements. We have diagonalized them. Okay. But that gives you the information only about the commutation relation between the Cartan subalgebra and the remaining generators, right? But now you can ask, what happens if I consider the commutation relations of these among each other? So far we have not done that, right? So that's the next step. What is the commutation relation between these? So to understand the structure. Okay, so I think that picture is there, and anyway these formulas are there. So if I can erase it now. So let us look at the commutation relations between this. So far we know. So far what we have done. C with C is 0, of course, because this is Cartan subalgebra is maximally abelian, and we have looked at C with the remaining guys. So the remaining generators, and we have diagonalized them. So you get again the same remaining one. Huh? And there are 6 of them. So this provides this, we have taken care of. But now we want to look at the commutation relation between remaining guys with remaining guys. No, that's what we want to do. So if I look at x alpha 1 with, let's say, x alpha 1, of course it is 0. X alpha 1 with x minus alpha 1, let's look at that. X alpha 1 was this, right? X minus alpha 1, when you take the minus sign, which I erased it, it will be the 0, 0, 0, 1, 0, 0. Okay, so let me just write. So x alpha 1 is simply 0, 1, 0, 0, 0, 0, 0, 0, 0. And the x minus alpha 1 is 0, 1, 0, 0, 0, 0, 0, 0, 0. Okay, I want to take the commutation relation. Unfortunately, I erased it, but you can see immediately. If you take the minus sign, this will become 0 and that will add up to give you 1. Okay, that's it. And because but already this was the lambda 1, lambda 2, lambda 3 provided, in SU2, poly matrices here in the upper 2 by 2 blocks, right? So this was sigma plus here, and this other one would be sigma minus, but sigma minus was 0, 1, 0. Okay, take the commutation relation, and what you find, let's just check. So we want to look at this here. And you find, if I multiply this way, so I will get here, first element will be non-zero and everything else 0. That is multiplying this way. Now multiply other way, right, in the commutator. So I multiply this with that, so I have a minus sign here, and this with that, so 0. This with that is 0, but that is not 0. So you get here 0, 1, 0, 0, 0, 0. Okay, which is the same as what we call H1, right? Because this minus that, so it becomes 1 minus 1, 0. Okay. So we are seeing that x alpha 1, x minus alpha 1 is, okay, can you erase this, is simply H1. Which was to be expected because these formed one SU2 subalgebra, right? So the sigma plus with the sigma minus gives you back up to some number gives you back sigma 3. That was it. Okay, and the same thing you can do for all of them. X. Let's just do also one more. X alpha 2, x minus alpha 2, and you should find that that's the same as x alpha 2 was this. I think you should find this is H2. Okay. H2. I mean, please work it out. I mean, because I've now erased all those matrices. So and if you take x alpha 3 with x minus alpha 3, then it will be a combination of H1 and H2. Okay, some particular combination, but that you can work it out what it is. But the important point is, okay, there are various combinations, but the important point is that when you take the commutator of the positive root with the negative root, the same root, the x's correspond to the same positive and the same negative root, not some other root, but the same root with a minus sign. Right hand side is always an element of Cartan subalgebra. You see, this is an element of Cartan, that's an element of Cartan, that's an element of Cartan. Okay, there's a reason for it, and let me just try to say the reason. I think I can use this. In general, you can ask the following question. If I have an x alpha and x beta commuted, alpha and beta are just two roots. So it could be alpha 1, alpha 2, alpha 1, alpha 3, or whatever. Alpha and beta are some roots, two roots. Then you can ask the question, is it, okay, this is going to be some element in the Lie algebra, right? Some element in the, because the commutation relation be some element in the Lie algebra. Complexified Lie algebra, by the way, because in order to construct these guys, we are multiplied by i's. So we are allowing the multiplication by complex numbers, just like what we did for SU2. So we are allowing the complex numbers. Then at the end, of course, you have to choose some real section to get SU3. You have to impose the condition that certain complex numbers are complex conjugate of each other. No? But at the moment, we are just treating it as a complex vector space. So we have this G here. Now you can ask the question, is it again, I mean, this is an eigenfunction with respect to the H1 and H2, adjoint H1 and adjoint H2. This is an eigenfunction with respect to adjoint H1 and H2. Is it also an eigenfunction with respect to adjoint of H1 and H2? Right? That's a natural question to ask. So let's look at H1 and add H1 and act on this. So what it will take you to? So this is an element. Well, add H1 by definition is nothing else but H commuted with whatever you have here, right? So in this case, we have this. So you want to look at that. Now I can use Jacobi identity. Okay. So what is Jacobi identity? It basically says that this is, if you apply that, it is going to be the same as H x alpha x beta plus x alpha commuted with H x beta. So repeat again.
Can also use the fact that adjoint is a representation, so we can write adjoint H1 as a adjoint commutator of adjoint H1 x alpha with the adjoint H1 x beta.
Yeah, you could write it like that. I think you can write it. Yeah. But you see, I mean, yeah, it is. You see, the representations are true. The representations are of course linear because they are linear vector space. But the commutator is not a linear action, right? I mean, but Jacobi identity you can use. This follows from the Jacobi identity. You see. How to say this? Yeah, you can check that the Jacobi identity implies that. But there's one easier way to remember this, because otherwise when you try to use Jacobi identity, this plus minus signs, you start getting confused about it, right? I get confused about it all the time. So the easiest way to remember is that this acts like a derivative, use the Leibniz rule. So you see, think of this as a derivative. This action is like a derivative, acting on these two. It's the same as taking derivative of the first guy, do nothing to the second guy, plus do nothing to the first guy and take derivative of the second guy. Exactly. So where the derivative action is what I'm saying is the commutation. Huh? So the Jacobi identity basically ensures that this taking the commutation relation is like taking a derivative. It's a Leibniz rule. Okay. So that's the easiest way to remember, because I get totally confused when I start looking at Jacobi identity, the signs, it's a bit, yeah. So if you do that, then, so if you accept this, then what do we get? This is the eigenvalue. So the first term, so this combination, this becomes alpha root, alpha h, right? For the h, so this will be a number. So given by the alpha is in dual vector space, dual to the is in the C star, and this will just give me a number.
Which one?
Okay, an arbitrary h. Arbitrary h is an arbitrary element of the kata. So h is an arbitrary element of kata. So it could be any linear combination of h1 and h2. So you get here alpha h times x alpha itself, and then you have this commutator, so x alpha x beta plus beta h x alpha x beta. Okay. So what we are saying, claiming what we have shown is that, so in general let's say, what we have shown is that this again is an eigenfunction, but with the eigenvalue alpha h plus beta h, because this is the same, right? So I can take it as a common factor. So this has an eigenvalue alpha plus beta. So now if I had chosen beta equal to minus alpha, right? That is what we looked at, no? Beta is equal to minus alpha, then this is 0. Okay. So that means add h commutes with that guy, right? But then we know, h commutes with that guy. But kata subalgebra is a maximal subalgebra, right? So therefore it must be in the kata subalgebra. Okay? That's the reason why we are finding that right hand side is always in the kata subalgebra. When we choose a root, the commutation of this guy with a minus, corresponding minus. Of course it won't be the case if I take x alpha 1 with x alpha 2, right? Because then, so suppose this is alpha 1 and that's alpha 2. Then you will get here alpha 1 plus alpha 2, no? Which is not 0. In fact, in this case, alpha 1 plus alpha 2 is alpha 3, right? So what we are seeing is that from this general discussion, we are saying, and today I should leave a little earlier to keep track of the time. So we are saying that x alpha 1 with x alpha 2 will be equal to some number. That number will be basically, this could be whatever it is. It could be some number, I don't know, times x alpha 1 plus alpha 2, which is the same as x alpha 3, right? Some number times x alpha 3. It is forced to be, because when I look at the commutation relation of h with this, I find it's alpha 1 plus alpha 2 times the same commutator, right? So this is an eigenfunction. Okay, eigenfunction with the eigenvalues being, so so this is, what I hope you understood, right? This object has the eigenvalue. If I apply h on that, add h on that, on this is an eigenfunction with the eigenvalue being alpha 1 plus alpha 2h. Alpha, these are linear, this also you can add. So therefore, which is the same as alpha 3h. So whatever it is, it has to be x alpha 3. Okay. This number, of course, could be 0. It might be, who knows? Abstractly, we cannot say, right? We have to just explicitly check whatever it is. But this argument is saying is that if this is not 0, If this is not 0, it is going to be proportional to x alpha 3. Right? Is that clear to everyone? So that is a kind of structure we are seeing. So, from this we obtain several conclusions. One, so if I have x alpha with x beta, this must belong to I don't know. Let's see if there is some notation given for this. Okay, let's see. I mean, this must be. This will have an eigen. So this will have eigenvalue alpha plus beta, right? But it could be that this root doesn't exist in your diagram, in the space of all roots. It could be, right? For example, let's see. The picture, unfortunately I erased it. Let me just show the picture again. So the picture was something like this, right? Alpha 1 here, alpha 1, then there was something like alpha 2 here, and then there was alpha 3 here, okay, and then minus alpha and so on, right? That was the picture of the SV3. Now if I had taken the x alpha 1 with x alpha 3, the commutator. Suppose I look at x alpha 1 with x alpha 3, this commutator, then this will be, if it is not 0, this commutator is not 0, then it must be something which has the eigenvalue alpha 1 plus alpha 3. But if you look at the alpha 1 plus alpha 3, it will be this vector, right? You add these two vectors, you get that, right? But that was not existing. That did not exist in your SV3 algebra, right? So therefore this must be 0. And on the other hand, x alpha 1 with x alpha 2, that commutator was going to be, actually it will be some non-zero number. You should check it. We already have the explicit form of this matrices, right? So using that matrix, check that this number is not 0. And it's in fact some non-zero number times x alpha 3. So computation of these two will give you this vector. I mean, sum of these two vectors gives you that vector. And so if it is not 0, it's going to be proportional to x alpha 3, right? But the question is to check whether this is 0 or not 0, this coefficient. Yeah? So please check that. What else can be? For example, if I take x, this is minus alpha 2, right? If this is alpha 2, I mean, it's a straight line. Not drawing correctly, but there will be minus alpha. There's a negative root for each of them, right? So minus alpha 2, minus alpha 3, minus alpha 1. So commutation relation between these two, x alpha 1 with x minus alpha 2, should be 0, because should be 0, because if you take these two vectors and add, you get something here, but it did not belong. It's not in the, right? So this should be 0, and so on. Now, this commutated with that, which should give you that. Okay. So this what appears on the right hand side is governed by these roots. You know? Of course, in this example, since we have explicit matrices, you can just work it out what the commutation. But what I'm saying is on the general grounds, you know, you see immediately this how useful the roots are, right? Yeah. So the general structure, what we are seeing is that this part is fine, and the general structure was I just write it here. So x alpha with x beta, there are several possibilities. Equal to 0. So if beta equal to minus alpha, then this belongs to the Cartan element. So this is inside Cartan. If beta equal to minus alpha, that is what we said, because if beta is equal to minus alpha, alpha plus beta is 0, so it is in the Cartan, right? It is equal to 0 if alpha plus beta is not a root, is not a root. And I'm assuming that beta is not equal to minus alpha. If it is beta equal to minus alpha, it is 0, right? And if alpha plus beta is a root, one of the roots, then it is going to be some number, I don't know which, let's call it n alpha beta times x alpha plus beta. This is some number. A priori, some of these numbers could be 0, right? But please check it, and you will see that every time this is a root, this alpha plus beta is a root, you get a number, a non-zero number. Okay? You can check that actually. Okay, so I think I'll just stop here now. Now let's see if there's something to say here. Yeah, so we'll continue with this tomorrow. I mean, for SU3, they didn't have to do all these things. All the matrices were explicit. But I'm formulating in such a way that generalization to arbitrary real algebra will become easy. That's the reason. Yeah. So see you tomorrow.